All right. Good morning, good afternoon, good evening, depend the place where you are currently. My name is Przemyslaw Maziarka, and I would like to show you a presentation on the reliability of the nitrogen physisorption of the quantitative assessment of the biochar specific surface area. This is the research which I conducted with Christian Verser and some other people. And yes, let's start with the presentation. In general, the idea of the production of the biochars, in general pyrochars from the bio-based materials is relatively simple. The concept is very simple. We start from the biomass, then we pyrolyzes this feedstock, and we obtain pyrolytic biochars which have a porous structure. And due to this porous structure, the material has a variety of the applications, starting from the agriculture, chemistry, and electronics. These are the novel solutions, which are mostly porous related. So, due to the porous structure of the biochar, we can apply this material in those novel solutions. And the question is, which types of pores influence the properties in these specific applications? The biochar have very wide porous structure, starting from the micropores through the mesopores to the micropores, and all of this specific kind of pores influence the applicability with in certain area. There are possibilities of qualitative measurement, so by the visual assessments with the optical or the electron microscopes, and there are also quantitative assessment measurements possibilities. Most of the research on the biochar focus on the chemisorption and energy storage applications because they are like the most advanced ones. And due to that, to assess the micropores in those regions, two types of measurement methods can be applied. The nitrogen sorption and carbon dioxide sorption. And when we look through the literature, we can observe that most of the data on the specific surface area of the biochars is measured with the nitrogen adsorption and then calculate with the BET method. There was several summaries of this property among which exists among the literature, and we can observe in there that the trend with the temperature is strongly inconsistent, and when we summarize the data, there is like strong deviations between the researchers, which are caused possibly by the feedstock, but it seems like the general trend should be somehow somewhat visible. Yes. Most of the studies also indicates existence of the peak at 600 degrees, at which the specific surface area of the biochar is the highest, and then with the increase of the temperature, the specific surface area drops significantly. And there was also very interesting research which measured the same biochar by the 8 different laboratories, and as we can see in here, the results were very different. The deviation among those results was very strong. Yes, and looking on those data, on the summaries available in the literature, we cannot really say how exactly we should produce the biochar in order to obtain specific surface area with wanted quantity. Yes. So due to that, we decide to conduct the research on that matter. We decide to use 3 different feedstocks, so wheat straw, rice husk, and wood cylinders, which 2 of them were pyrolyzed in the TGA, and the third one, due to the larger size, was for pyrolysis of this material was used single particle reactor. They were pyrolyzed in 4 different temperatures, 4, 5, 7, and 900 degrees. Then biochars obtained from the specific matrix point of the research was homogenized, so it was ground to reduce the influence of the macropores diffusion during the measurement. And then the samples were measured with the nitrogen and carbon dioxide adsorption. all of those information that will be provided in this presentation will be found in future. You will be able to find them in the publication with the same name as this presentation. We are currently after the first revision of this manuscript, so possibly the publication should be available soon. Yes, so for the nitrogen, we use the P2P0 range between 10 to the minus 3 to the 99, which gives roughly pore size distribution between 0.7 and 50 nanometers. And for the calculation, we use the pore non-specific method, so the BET, the standard one, and the pore specific method, which allows to obtain pore size distribution. So more or less the volume absorbed at certain range of the pore size. With the carbon dioxide, we use also the typical range of the P2P0 from 10 to the minus 4 to the 10 to the minus 2, which corresponds to the pore width between 0.35 to 147 nanometers. And as well, in here we only use the pore specific method, so the Grand Canonical Monte Carlo method. It needs to be stressed that those methods are interchangeable. So the results for the same range should be similar for the same range of pore width should be similar from both methods, as it was presented by Rawikowicz at 2000 et al. So the basics of the BET method, this is the equation which Browner, Emmett, Teller method uses, and there is some restrictions with its use. In literature, when we read through the methodology of the assessment of the specific surface area, usually there is not a lot of information provided in those sections. So there usually, if there is any information, there is a P2P0 range on which the absorption was made, and not more than that. So just to be on the same foot with everybody, I will just briefly explain how to appropriately use BET method. Yeah, so there is like 3 main restrictions with its use. So the P2P0, which is used for the calculation of the specific surface area with BET method, should be linear on the BET plot. So when we have in the bottom there is P2P0. So when we put on the plot these 2 quantities, we can only use the place where the plot is linear. The second thing, which is usually omitted, is that on the Rockerose plot, so for those who use Quantochrome software, it's known as BET assistant plot. On this plot, only P2P0 range can be used at which this quantity is increasing with the P2P0. So only this part of the P2P0 can be applied. And the third is that those ranges should be the same between BET plot and the BET assistant plot. If those restrictions are not fulfilled, the C value, which is calculated also by the BET, is not positive. Then it gets a negative value. And it cannot have negative value because the C value corresponds to the energy of the monolayer adsorption, and the energy of the monolayer adsorption cannot be negative. That is physically impossible. And in the literature, the Browner, in his initial publication, he indicated that most of the materials should be measured between P2P0 range 0.05 to 0.35, and typically it was shortened to the range 0.1 to 0.3. But when we gonna read through the UEPAC's technical report, they strongly highlight that for the microporous materials, P2P0 has to be manually adjusted. Otherwise, the C value is going to be negative. When we're going to go through our samples, for the result from our samples, can be observed that the point at which BET can be calculated changes with the production temperature. More or less, it's strongly related with the amount of the micropores that are assessed by the nitrogen adsorption. And simply speaking, by this red line indicating here the maximum range from which BET can be calculated, and the more this line is to the left, the more microporosity is in the sample. So if we do not adjust the P2P0 range, in case if our biochar has strong microporosity, we introduce the error to the calculation. Not only we obtain this negative C value, but the value of the specific surface area is errorless. There is some error is in there. And if this red line is more to the left, yes, and we use still the standard range, we introduce more error to the obtained data. So if we have very strong microporous material and we use standard range, yes, let's say for the 700, we introduce almost 30% of the error. If we observe that, if we will take in account that the microporosity is the porous structure which is strongly the strongestly related with the specific surface area. So for more or less this scenario, we can observe like 500 meters square. And if our calculation have like 30% of error in there, it's very significant value, which further on gives us a strong deviations in the final result. In general, the tendency can be observed from the summary of the data that was available to us that the stronger microporosity, the lower the range from which the BET can be calculated, and the larger surface area. So if the material is very microporous, then definitely it's gonna have a larger BET area. Since the BET method is non-pore specific, we cannot really say more about the porous structure inside of those biochars. So let's take a step back and look into the isotherms obtained by the nitrogen and carbon dioxide. I will maybe quickly mention what is the hysteresis and what means that hysteresis is open. The hysteresis means that there is lack of the agreement between the adsorption and desorption, and the open means that the initial point of the adsorptions do not meet with the final point. For the biochars, the open hysteresis is very well known during the nitrogen adsorption, and for our sample, most samples from 500 degrees to the 900 degrees show very strong open hysteresis. On the other hand, when we check the carbon dioxide isotherms, we don't see that strong hysteresis, which it's the first point that interested us. Why is that? And the second interesting property that can be observed in here is that for the nitrogen, rice husk and beechwood, along with the temperature, increased the volume that was absorbed during the measurement, and then at the 900 degrees, this volume reduced. That was not observed for the wheat straw. And on the other hand, when we check the carbon dioxide isotherms, we see consistent trend with the temperature for all the biochars from all the feedstocks, that with the temperature, the volume adsorbed increases up to even for 900 degrees. That was very, that was the first point that really interested us investigating this data set. We look closer to the pore size distribution of the rice husk, and we observed that the most of the volume that was absorbed at 5, 7, and 900 degrees was located in the microporous region. Overall, from broad data set that was available to us, we observed that from 500 degrees to more or less 900 degrees, most of the volume, total volume assessed by the nitrogen is located in the microporous region. So that would mean that for 5, 7, and 900 degrees, specific surface area is mostly dependent on the micropores and assessment of those structures. When we compared the results for the same range of the pore width between carbon dioxide and nitrogen, we observed that for 400 and 500, volumes assessed in this specific range by the nitrogen was much, much lower than carbon dioxide. But then for the rice husk and wood straw, volume was or similar or even higher for the nitrogen than for the carbon dioxide. Which was very strange due to the information provided in the literature that nitrogen at 77 Kelvin have very strong problem with the diffusion, especially into the smaller pores. And the carbon dioxide measured at 273 kelvins do not have this problem. So that's really interests us. What is the cause of that? That at 700 degrees, we observe such inconsistency. In the literature can be found very interesting study by Blazer et al. From 2016, who simulated the absorption stress by the different gases. And from his results can be observed that within the range, the typical range of P2P0 at which nitrogen is used, the stress which gas cause on the micropore walls is very strong. Yeah, this is the red line and the green line. On the other hand, when we see the carbon dioxide within the range that we used, the lines are not that visible. That means that stress is not that high. To assess the difference, how should I put it? To investigate it deeper, we decide to make sequential measurements on the biochars, on the rice husk biochar especially, on different temperatures. So we use the nitrogen, carbon dioxide, nitrogen, and so on in three sequences. And then we checked how the pore size distributions differ between each other. And what we found out that at 400 degrees, there is not a lot of difference between the pore size distributions, which means that the structure is not very prone to show any distortion of the pores. At 700 degrees and at 900 degrees, the difference were very strong for the nitrogen, but for the carbon dioxide, not as such. In general, for the nitrogen and carbon dioxide, the strongest deviation were observed for the biochars produced at 700 degrees, which is the point at which most of the research says that there is a peak, and there is usually the problem with measurement of the materials produced at this temperature, which also give us a hint to investigate that point further. In general, we focused then on the properties of the biochar itself, because it seems like we know that nitrogen induces some kind of stress, carbon dioxide doesn't. But the question is why at 700 is the most visible, yes? When we when we imagine how the biochar carbonaceous structures look like, it's made by the base structural units, so more or less the graphene sheets ordered in some way within the carbonaceous structure. The summary of the results from the XRD indicate that between the 500 and 900 degrees, the spacing between the graphene stack reduces. Also, the size of the BSU unit increased from the 500 to 700 degrees. That, on the other hand, changes the mechanical properties as well as true density of the biochar. In general, from the research made by the Paris et al. From 2004, we can observe that at 600, 700 degrees, the ducticity index is the lowest, while the elasticity and the hardness of the biochar structures do not reach its maximum value. Yes, that is the strong indicator that the carbonaceous microstructures can undergo deformation at this temperature region, which also transmits to the lack of the rigid yes, to ability to deform of the micropore structures. Going step deeper into this into this area, it's clearly it's well known that with the temperature the BSE unit increases. Yes, but in biochar the structure is not planar, but it's in a 3D. So actually the structure looks more like that on the bottom. So there is like interconnection between the BSE units, and there is also stabilization. There is like long range interactions between the BSE units within the carbonaceous matrix. Yes. So if we take into account also that at 400 degrees, most of the cellulose and the hemicellulose is already degraded, then the only biocomponents that is present in the biochar is the lignin at 400 degrees. Yes, and more or less the whole carbonaceous structure is based on the fundament produced made by the lignin. Those BSE units showed above are the images of that are mostly based on the precursors which have very low oxygen content. On the other hand, biomass have very high oxygen content initially. Also, the lignin have a very high content of the oxygen. And if we will, when we see the changes in the H2C and O2C ratios, we can observe that up to the 500-600 degrees, most of the oxygen is released from the structure. Yes, at this point, most of the oxygen is released, but the H2C ratio still its value getting lower along with the temperature. Yes. The content of the oxygen in the precursor causes that biomass in general do not undergo the graphitization process. What does that mean? That means that its organization type is known as a hard one. On opposite to the carbon structures like from coal, which are known as a soft one. What's the difference? What difference does it cause? The oxygen and heteroatoms in the structure leads to the stabilization of the BSE unit because due to the long range interactions between the BSE units. So in the moment when we release strongly the oxygen from the structure and the structure doesn't really form the carbon crosslinks, that means that the BSE units are not stabilized very strongly, which gives them a high mobility within the structure. As we can observe on these pictures from the made on a TEM basis, at the 600 degrees, we have very small BSE units which are not strongly interconnected between each other. Yes, that means, and then at 800 degrees, when the temperature increases, the interconnection, the carbon crosslink starts to appear. That clearly indicates that those structures around 600, 700 degrees will not be rigid. So any stress induced by the adsorption will cause the pore deformation in them. To quantitatively assess the difference, some additional measurement has been made, especially for the wood char, and we observe in there that in this microporous region, there is a huge difference between the consecutive measurements. However, when we increase the pore size from higher than 1.47, the deviation between the result is relatively small. But if we will only use the nitrogen, the nitrogen data for calculating specific surface area, we can observe that between the first and the second measurement, the deviation is very strong, yes? And it is caused mostly by this micropore region. So the more or less the region then where the pore deformation can occur. On the other hand, when we compare the carbon dioxide data, we do not observe that strong deviation for the microporous region, mostly because the stress was much lower, even though that structure was prone to undergo deformation. The actual stress wasn't that high to cause the deviation among the results. So our idea in general was to do not use the nitrogen data for the microporous region assessment and use only this region that is that doesn't have a strong deviation, and for those micropore region use the carbon dioxide data. So we cut off from the nitrogen the micropore region and we add carbon dioxide, and out from that we calculate the pore size distribution. And that was the assumption that in that way we're gonna obtain very we're gonna increase the reliability and the reliability of the data. So on the 20 data points that we had, we calculate the specific surface area based on the carbon dioxide and adjusted nitrogen pore size distribution, and we compare it with just simple nitrogen adsorption data. So the full pore size distribution from the nitrogen adsorption. As you can see, for the carbon dioxide, the trend with for the carbon dioxide and adjusted nitrogen, the trend with the temperature is very consistent with the temperature. There is no peak really visible in here. Also, the deviation among the points is homogeneous. That means that none of the points have some additional, some uplifted, some enhanced error inside. On the other hand, from the nitrogen, as we expected, the point at 700 degrees show very high deviation, only in that point. Other points do not really show that much deviation. In general, due to the larger specific surface area assessed by the carbon dioxide, from merged data sets, we can observe higher specific surface area, but on the other hand, it seems like it's more reliable in here. Then from the much larger data sets, we calculate specific surface area on bed terms, on the DFT terms for the whole range, so between 0.7 and 50 nanometers, and we calculate the specific surface area only on the adjusted pore size distribution. BET and DFT in that case show very similar trend, but also peak at 700 degrees and very strong deviation in here. So for the 62 points that we have, the deviation between the points was very significant. And we assume that this was most related by the not accurate assessment of the micropore region below 1.47. Yes. On the other hand, when we use the adjusted method, then we can observe homogeneous deviation and very consistent trend. And as well, we do not see this artificial peak, which presumably is caused by the adsorption stress and proning and structure to be prone to undergo the pore structure change. So let's sum it up. I think 40 seconds still ahead of me. So in general, we found out that biochar seems to have not fully rigid carbonaceous matrix, especially when produced between 500 and 900 degrees. Therefore, the microstructure of those shards is prone to undergo the deformation, especially when the stress by the adsorption is induced. In general, we suspect that adsorption with nitrogen at 700 at 77 Kelvin induce a very strong stress onto the pores, which cause the pore deformation. And that is also related with appearance of the open hysteresis during the nitrogen adsorption measurements. On the other hand, carbon dioxide do not indicate that strong stress, which can be also observed by the lack of the hysteresis during the measurement, and also the reliability of the data that is obtained by this consecutive measurement, the sequential measurements. In general, due to those issues, the data from the nitrogen adsorption should be from the whole pore size distribution. The data regarding the pores lower than 1.47 nanometer should not be used, because they can be strongly biased or strongly errored. Yes, and if there is possibility, those range should be assessed by the carbon dioxide. In general, when we assess the data from the nitrogen adsorption, we shouldn't really use the non-pore specific methods like BET, T-plot, alpha S, because there is no possibility to adjust pore size distribution in those methods. So they will be always biased by the errorless measurement with the nitrogen, as well as by the lack of the rigidity, by the biochar structure being prone to undergo deformation. Yes, so it's strongly advised to use pore specific methods like DFT or the Monte Carlo method for assessment of the pore size distribution. And yes, that would be all from me. Thank you very much for your attention. If you have any detailed question or something else that you would like to say to us, you can contact me or Christian. For the future reading, I strongly recommend to wait a bit for this publication. There is a lot of information that can interest you regarding of the specific surface area assessment of the biochars, and relatively soon there's going to be available publication with very similar topic, which is focused more on the tailoring of the pore size distribution of the biochars, especially with the focus on the energy storage application. So thank you very much, and all questions are welcome.
Thank you very much, Przemyslaw. Really nice and interesting topic, I have to say.
You're co-author, so.
So you got two questions from Robert. The first is, are you aware of Sigmund et al.'s paper about the degassing influence of on biochar surfaces?
Yes, I am fully aware of this. We also contact Mr. Sigmund. And we have his data. He allowed us to use his data from his measurements, and it's included in all these summaries that we used. In general, we base strongly on this publication, but we didn't pursue very strongly the topic of the degassing. We focus on something else than the focus is of Mr. Sigmund's publication.
The degassing temperature that you used, can you share it with us?
We used the degassing temperature 180 degrees, and we did the degas 24 hours prior to the measurement.
Close to the recommended range, right? I think Sigmund recommended 200 degrees Celsius to get stable readings.
Yes, in general, the temperature should be high enough to remove all the adsorbed compounds like moisture or gases. But on the other hand, the degas temperature shouldn't really remove the tars that are adsorbed on the biochar, because in typical application of the biochar, no one is degassing the material prior to its use. So that is like kind of balance that needs to be obtained, yes, in that manner. So in general, if you have a biochars which is produced 350, 400 degrees, the temperature 180 or 200 degrees is not a problem. On the other hand, when you try to assess the hydrochar, which are produced like 180 or 200 degrees, the temperature definitely should be lower. That's like my point of view on this degassing. Of course,
but I think hydrochars are not really biochars, right?
No. They have totally different structure. Yeah, I've just only mentioned that the degassing temperature can have very strong influence on the afterwards assessment, on the outcome.
Yeah.
Especially as the Sigmund showed that for the carbon dioxide that doesn't really change much, but for the nitrogen it strongly cause strong deviation in the result. For the same temperature production, but degassing with a different degassing temperature.
Thanks, Przemyslaw. And the second question from Robert was about the residence time used to produce the biochars.
If I remember correctly, for the TGA, there was 5 minutes, Christian, yes?
No, actually, it was all 10 minutes beside.
For the TGA, all materials were paralyzed with the 10 minutes residence times after reaching the final temperature. For the cylinders, the situation was somewhat different because that was a larger particle. So there was a restriction on the heat transfer inside to the center of the sample. So for the 400 degrees, when the heat transfer is relatively low due to the small difference in the temperatures, the actual temperature of the conversion was 15 minutes. For 500 and 700 degrees, it was 10 minutes. And at the 900s, the sample reached the temperature 900 at its centers after 5 minutes. Of course, we checked after reaching this temperature, after reaching the steady mass of the cylinders, we still wait like 10 seconds to be sure that deviation of that the mass doesn't really change. I hope that answers the question.
Thank you. I was just wondering if you keep the residence time constant at higher temperatures, isn't there a chance that the pores can start to increase in size?
There is possibly, I understand what you have in mind, that the structure after, let's say, when it's reached the temperature, the development of the structure also needs some time, yes? So then when it's reached the 900 degrees, then it's not fully, let's say, stable, thermodynamically stable. And then with the time, it gets to its final form, yes? But on the other hand, at this point, it's very hard to state that, because there is not a lot of research on this manner. So we cannot really, I wondered about this, but I couldn't really find any reliable, let's say, publications that could confirm it or say that it's nothing as such happens. Yeah.
We have another question from Juan. Are nitrogen adsorption BT method reliable to measure biochar surface area in the order of 10 to the -1 square meter?
No, not at all. Not at all. In general, it's assumed that for specific surface areas around like 10, 20, in that range, the mass of the sample have to be have to have mass around like 1 gram or even more. Yes, like 2 grams, because that low value indicates that there is not a lot of porous structure inside of the material that is assessed. That means that most of the specific surface area assessed then by the nitrogen is located on the surface, because adsorption takes place on the surface of the material as well as inside of the material if there are porous structure inside. In general, if there is very low specific surface area assessed by the nitrogen, some additional measurement with the carbon dioxide can be made, because maybe the pore size and size are so low that nitrogen couldn't really enter those. But in most of the cases, that indicate rather that sample is not porous.
Thank you. Then Shabib asked, can I know the main effects of feedback and residence time in the production of biochar?
Regarding of the residence time, there is not a lot that it doesn't have a lot the strong influence on the data, at least from the knowledge that I have. So that would mean that residence times the most important, let's say, production-wise, this is quite important parameter, because when we use a larger production sites like the reactors, then we need to be sure that the material is fully converted at the certain temperature. That's why we have to keep the certain residence time, and we need to check the properties of the material. Yes, but then after we obtain those properties in the homogeneous way, then increasing the residence times shouldn't really change much the properties of the material itself. Yes, the second part of the question, the feedstock wise, at this moment it's very hard to judge how different feedstock influence the specific. What is the relation between the feedstock and the specific surface area? Because most of the data that is presented in the literature can be biased or can be not reliable. So making any statements basing on this can give you a erroneous conclusion. So I would, at this point, I would rather do not suggest to make those kind of indications how which feedstock influence the specific surface area. Yes.
And last question. I mean, you have a couple of minutes to write another question, but for now, the last question is: ash content of char an issue in BAT measurements?
In BET measurements, I strongly, after this presentation, I strongly encourage everybody to use rather use the phrasing of nitrogen adsorption and carbon dioxide adsorption, and then specific surface area calculated with BET method or with any other method. Because that creates a lot of confusion, because BET is a calculation method, it's not a measurement method. That is a very strong difference. Yes, but what's the influence of the ash? In general, that depends on the ash. So if there is the porous structure inside of the inorganic material within the biochar, definitely that will be assessed. In this study, we didn't put a lot of focus on that. From one hand side, the wheat straw and the rice husk contains a significant amount of the ash in the biochar, but on the other hand, as is presented right now on the screen, the woody and husk biochars behave similar, even though that wood and husk have very strong difference in ash content, and the straw-like, so wheat, bamboo, behaves differently. So it can be more or less related to ash. but also can be related to other composition features of those biomasses. So at this point, I cannot also make any conclusions regarding of the char. Definitely, if the content of the char is like 50, content of the ash is like 50, 80%, then we can be sure that that amount of the carbonaceous material is lower, and then overall per mass, we're gonna obtain much less pores. Yes, that's like general rule.
And maybe to add on to that, there are some inorganic matters that are more volatile, like potassium. So when you go up to 900 degrees, you volatilize certain ash components, and that can create also pores, right?
Yes, of course. Yeah, there is also we have to also keep in mind that around 700 degrees thermodynamically degradation of the inorganics can happen. Below that temperature, we can have also within the biochar the organic metallic compounds. Yes, like salts and such, like organic salts, which can also degrade with the temperature and also produce inorganic materials which have totally different morphology and can also change the specific surface area that we would like to observe. Yeah.
And act as a catalyst maybe as well.
Yes, as well. But those also are involved with the formation of the biochar structure itself, of the arrangement of the carbonaceous of the BSU units.
You got another two questions. So the first one is from Hugh. How valid is the monolayer assumption and equal adsorption energy assumption of the BET method, especially with respect to nitrogen measurements?
I will be honest fully with you that I'm not very deep in the, let's say, theoretical fundamentals of the development of the BET method. So I cannot really very precisely address this question. That I will be honest. Overall, this is theory as, in my opinion, as any other that can be valid or not. There was like plenty of validation study on this one. So since it's so widely used and also was widely used, especially in the material sciences, then I would say rather yes, or how valid, like should be valid at least.
Maybe I can add to the monolayer assumption. So we can at least see from the C parameter values we got from our data set that with some biochars you go up to 1,000 or something, and as a general rule of thumb we know that above 100 or 150 we can assume that there is no monolayer assumptions, but instead there is already micropore filling before a monolayer is reached. So I would say that's I would say that the assumptions from the BET are really there to you have to keep in mind that it's an averaging technique, I would call it. It tries to get something out of a really easy method, I would say, or at least easier than the DFT models.
Absorption in the micropores and in general in porous material is kind of complex yeah, phenomena, and the BET method is treated very lightly, let's say. So it's like the quantification of the results that was obtained by the nitrogen absorption, but if it's really actual value of the specific surface area, then that is the question.
And there's another question from Vera Bodu. The molecular size of CO2 and nitrogen, their dipole momentum and diffusion rates in tortuous micropores and nanopores make the difference. Use of other permanent gases may also give some insights to study the steric hindrances and be able to explain the differences.
I agree with this. That's very valid point. But how should I put it? In my personal opinion, the diffusion is the key in here, because the nitrogen measurements take place at the liquid nitrogen temperature, so at 77 kelvins. On the other hand, carbon dioxide measurements usually take place at 0 degrees Celsius, so 273 kelvins. So more or less, we can imagine that we measure something at 0 degrees Celsius and 200 degrees Celsius. The temperature is much higher, so the diffusion is much strongly influenced by that. And this diffusion problem can also be a factor why the sorption stress from the nitrogen is so high. With the dipole momentum, yes, of course, that's also relevant. There was also a discussion if the carbon dioxide should be used on the materials that have some not homogeneous structures. So if there is some oxides on the surface, some metals on the surface, because that can induce the chemisorption of the carbon dioxide, and that can lead to the not reliable measurements. Yes, but those are the things that needs to be further investigated and quantified if we would like to make a strong statements on their influence.
And another question from Ronald Larson. How does your work influence economic competition between Biochar and its competitors for absorption and absorption and adsorption, I guess?
Level out, I think it's gonna level out the field, because when we look on the, let's say, activated carbons, yes, and we check the studies on this material, we can observe that results are reliable in there. There is not strong hysteresis on their measurement when we use the nitrogen, yes. So then we can assume that some kind of production parameters can influence the specific surface area in certain kind of way. With the biochar, to this point, it was very hard to judge if the production parameters changes the specific surface area or not, or it is like measurement related. Yes. That strictly means that from that point, when we have a reliable way of the assessment of the biochar, we can then start to engineering it to the way, in the way that further on can be applied for more novel applications. Yes, while activated carbon reached that point a long time ago. So then at least we more or less level the field of the assessments. And we are at the same reliability with the specific surface area, but also the pore size distribution, which is crucial for some kind of applications. And then I think this, at least I assume that this study should enhance or give some momentum to the biochar studies. Especially for the tailoring its properties. So then the material will be better for the use in the novel applications. Yes, and yeah. If that have any sense, if my answer have any sense.
So I would say last chance now to unmute yourself and ask Przemyslaw a question. And otherwise, I think we are well on time. Oh, actually well over time, but
of course we are over time.
So if you have any question, just unmute yourself or type really fast.
Maybe it's related to Ronald's question. if I understood it correctly. Did you guys include a positive control in your studies? Like you use activated carbon that is made from coal, or activated carbon that is made from, I don't know, coconut, and
No,
saw the
no,
same behavior happen?
we haven't include this material, mostly because the production is completely different. When the material undergoes the activation, one point is that not a lot of producer gives you any information about the production temperature. Second thing is they do not really provide information which type of gases they use for the activation. And those two things can very strongly change the carbonaceous structure inside of the material. That is why most of the activated carbon do not show this nitrogen open hysteresis during the adsorption. Yes, so the comparison of this material will not give us any insight really in that way. Yeah.
Maybe to add, so I did a lot of nitrogen adsorption on normal activated biochars and activated carbons, and you don't see the same effects with some chemically activated one, but the moment you go with CO2 at 800-900 degrees, you don't see this open hysteresis anymore, or you see it really a lot slower. So I think there's not a good positive control available right now, which is in principle the problem with biochar research, that we don't have standardized possibilities to actually check characterization methods.
Also, that's why Edinburgh University, especially the UK, what's the name of the institute of your institute?
That is the standard biochars, yeah. So we
yes, exactly.
Add one of them, but wheat straw and rice husks are actually part of the standard biochars.
More or less, that's the new standard. Yes.
That's actually
Yes.
Yeah.
Okay.
All right.
Anyone else with a